All right, you guys, how's it going? We are going to do some applications of radian measures. So we have two new formulas that you need to start kind of thinking about. The arc length formula and the area of a sector formula. So these are formulas and things that you found area and length of when you were in geometry class, except now we're using radians instead of degrees. So just keep that in mind that theta for these two formulas are going to be always in radians. That might mean that you need to convert, like this one is in degrees. You should turn it into radians first and then use the formulas. And just keep in mind, we use an S for arc length and we use A for area. So make sure that you're differentiating between these two formulas. This first example here is asking for length of the arc. So we're going to be using this top formula. But then later on in the notes, what we're going to be using is the area formula. So pay very close attention to what the question is asking, of course. So I'm going to dive right into this first example. A circle has a radius, so we're going to use this for our R. Find the length of the arc intercepted, so length of the arc, this is the formula we're using, by the central angle having each of the following measures. So the central angle is the angle that intercepts the center of the circle, and so that's what we're given here in radians and here in degrees. And so what I'm going to do first is start with my formula, S equals R theta. In this case, my radius is 18.2. It's up here in the problem. And they're asking me for the arc length, so I'm going to leave S as my variable, but I'm going to plug in 18.2. And my radians is 3 pi over 8. And that is already in radians because it is labeled here, radians. This is a degree symbol, so I'm going to have to convert that before I plug it into my formula. In this case, since the radius is a decimal, I'm going to use 3.14 for pi, and I'm going to multiply it all out, or you could use the pi button in your calculator, but it gives you 21.44 centimeters. And that's when you use 3.14 for pi, or the pi button. So we're going to be rounding in that one. Math Excel and the directions on worksheets and tests and stuff, I'll be clear whether I want you to leave your answer as exact, meaning it'll have a pi in it, or rounded. But in this case, since we started with a decimal in our problem, it would be weird to have a decimal and a fraction with pi as a final answer. So I'm just going to round everything, in this case, to 2 decimal places. But like I said, Math Excel and worksheets and stuff, they will be clear. So the first thing I need to do for letter B is convert this to radians. So remember, the conversion factor is pi over 180. And then you can reduce the 144 and the 180, and you get 4 pi over 5. And this is radians. So this is what's going to go into my formula. So this is what I was talking about up here. You might need to convert depending on what you're given. Here we were given degrees. So again, I'm just going to use the same formula. It's a very simple formula, S equals R theta. My radius is still the same, 18.2 for the whole problem. And I'm using 4 pi over 5 radians. And in this case, again, using the pi button since our radius is a decimal already. And rounding to 2 decimal places, 45.72 centimeters. And so what does this mean? What numbers did we just crunch here? So remember, length of the arc. Basically what it's asking us for is we have a circle here and we have some sort of degree in our central angle, and it's asking us for the length of this arc here. So like if it were a string and you were to straighten it out and measure it, that's how long it would be. So keep in mind that's what length of the arc is actually talking about. Let's go to this next problem. So a pretty common type of problem that we're going to be seeing, like real life type of stuff, is the distance in between two cities when you are given latitudes for the city. So Reno 40 degrees north, LA 34 degrees north. We have a radius of the earth, find the distance between the two cities. So this is the type of problem that we're going to kind of set up. We have our north-south line, and here is our east-west, and it says that Reno is 40 degrees north. And so the way that that's kind of pictured is, picture this as like the world, and I have the radius of the earth here. And so Reno is 40 degrees north, so that means I'm going to draw my arc this direction, 40 degrees. And Reno is out here. Okay, so this is 40 degrees. And then it says that of LA is 34 degrees. So LA is not quite 40 degrees, it is 34. I'm going to put LA here. This degree is 34. So it's a little bit of a weird picture, but basically what I need to figure out and what I need to like zone in on is this right here. The distance between LA and Reno. So if you can kind of picture that, what I'm trying to find is this right here. how long is that? And I have my radius already, that was 6,400 degrees, but what I need to figure out is how big is this angle right here. So you're taking this 40 and you're subtracting the 34, and what you're left over there is 6 degrees. So I'm going to write that out. Find the degrees between 40 and 34. And we just subtract that, so 40 minus 34, that means that there's 6 degrees there. And then, of course, I need to convert that to radians, so multiply by pi over 180, and that reduces, 6 goes into 180, it gives you pi over 30. And so now finally what I can do is use my arc length formula, the one that we used on the front page, S equals r theta. I have my radius from the problem, 6,400, and my theta is pi over 30. And so again, using the pi button in the calculator, that's going to give me 670.206 or 0.21 kilometers. And the reason I'm using kilometers is because it wasn't miles that was given in the problem, it was given kilometers. So make sure that you're just using radians for the theta in the problem. And what I had to do was draw kind of a weird picture, but that's typical when you're given like latitudes of cities and stuff like that. So. Okay, another really common problem, 2 gears are adjusted so that the smaller gear drives the larger one. So this is super important in like engineering and architecture and physics and all kinds of stuff that we've been talking about in class, about the reason why we're doing all this radian nonsense and applying our geometry even further into more difficult problems. Rotates through 225 degrees, through how many degrees will the larger gear rotate? So if you can picture that, if this gear rotates 225 degrees, so not a full circle, but you can tell that this gear is much bigger and it's not going to rotate as much as 225 degrees. So I wrote out a little bit of an instruction for you. We're going to first find the arc length that the small gear has when it rotates 225 degrees. So basically how much of this circle is going to touch the bigger gear when they rotate together. So I need to first find that small arc length. And that's going to tell me basically like through how much of the circumference that circle is going to rotate. And I'm going to apply that to this one. And so that's going to help me figure out how many degrees this one had to turn, because they are going to touch in the same exact length of arc, basically. So another thing that you need to keep in mind before I go too far into this problem, we do need to turn this into radians. So 225 degrees times pi over 180. 225 over 180, I would start just by dividing by 5, but it ends up being 5 pi over 4. So that's what I'm going to have to use in my S equals r theta formula, and this is for the small gear first. So I'm going to start there. I need to first find the arc length. The radius is 2.5. Oh, that's given on the picture. Duh, right here. 2.5 is the radius for the small one. 2.5, and I'm going to multiply by that by the 5 pi over 4. And I'm going to use my pi button in the calculator, and that gives me 9.817. It's important to use a lot of decimal points here because we aren't finished with the problem. If I would round here too soon and then round again and then use 3.14 instead of the pi button and just continue rounding too much, my final answer is going to be inaccurate. So let's use a lot of decimal points. It's even better if you just leave this number with a bunch of decimals in your calculator. But now I'm going to move on to the big gear. And I'm going to use the same formula, S equals r theta, but this is the arc length that it rotated with the smaller gear, so that means that my bigger gear is going to rotate that same exact amount. So I'm going to use 9.817 equals, and I have a radius of the big gear, 4.8 theta, and just solve for theta, and that's going to be theta equals 2.045. And so keep in mind the formula of S equals r theta gives you radians, and make sure you pay close attention to the problem because this asks us for what are the degrees of the larger one. So one more conversion gets us the final answer. So remember how to convert radians to degrees. You multiply by 180 over pi. And that means that my theta equals 117.17 degrees. I know that's kind of a longer problem, but there are going to be a few different gear types of problems that you're going to have to work through. So I have like the step instructions here. Step 1 is to find the arc length of the small gear, and that's what you're given. And a way to like adjust this problem to be a little bit different is maybe they would tell you how much the big gear rotated, but you would apply the same exact logic, then you would apply that to the smaller gear. So you might reverse these two if it was a different type of problem. But then once you find that arc length, it's the same formula, and you apply that to the bigger gear, but then you just have to convert your radians back to degrees so that you answer the question here. Okay, very last problem, you guys, and then we will do some more in class just to make sure you're all on the same page and we've got a good understanding of what's going on here. But here we are, the very first problem using the area of a sector. So that's a different formula. So find the area of a sector of a circle with this radius and this arc length. So what I need is the degrees. I have a radius and I have an arc length, so what I'm going to have to use first is the arc length formula because that's what I'm given here. So 3.75, the radius is 10, I don't know the theta, so I'm going to solve for that, and I get 0.375 equals theta. And now what I'm going to use, and that's in radians, the formula gives me radians, so that's good. I don't have to convert it because this question is asking me for the area. So now I'm going to use my area formula, 1/2 r squared theta, and I don't know the area, that's what I'm solving for. The radius is still the same, it's 10, don't forget to square it, and use the radians from the arc length formula that we already calculated. And so when you crunch that whole number, we get 18.75. This is an area problem, so make sure your units are squared, and this is feet squared. Okay, so that was our one formula where we actually had to use both of them, but we ended up using the area formula for the first time in these notes. Okay, we will do a couple more problems like this in class tomorrow just to practice, but here's kind of your basic intro to arc length and area formulas. Just keep in mind the big note, you guys, is that theta is always in radians for this. So you either have to convert or you're going to have to convert back if the question asks about degrees. Okay, thank you for watching. Like I said, we'll do some more problems in class tomorrow. Bring your questions to class, and I'll see you later. Have a good night.